Okay, so basically what Zener diode is, first of all let us understand the concept of Zener diode. So this Zener diode is a diode, special diode, which is made to work in the reverse bias. So in this, usually diode doesn't work in reverse bias, and if you apply a certain reverse more than a certain value of the reverse bias, then diode gets breakdown. So this particular Zener diode is for the reverse bias kind of applications where you need to work on the reverse bias. Okay, let us go further. In this diode, this is the symbol of the diode. So the symbol is similar to the normal diode, but the difference is what this one, this Z symbol here. This Z symbol is because of the Zener word. So this Zener diode represent the Zener, this Z symbol is because of this Zener diode, and Z can also be like this. So both means there are some books which show symbol of Zener diodes like this. Okay, so either you can use Z like in this one, this symbol, or this symbol can also be used for the Zener diode. The look means how does the Zener diode looks? Zener diode looks like this. So this is one photograph of Zener diode. So this photograph is similar to the normal diode photograph, but there is working is different from the normal diode. Okay, so this is a special p-n junction diode which works in reverse bias. That is what I have told you, that this is a special p-n junction diode, but it works in reverse bias. Second thing that you must know, that this is a specially designed for reverse bias operations in forward bias. It works as a normal diode, and the breakdown voltage of Zener diode is set carefully by controlling the level of doping at the time of manufacturing. So if you want to change the Zener voltage of a manufactured diode or already available diode, you cannot change the Zener voltage. The Zener voltage of the diode is changed by the doping level at the time of manufacturing itself. So if you already manufactured diode, if you want to change the Zener diode, then you cannot change. Other thing is that Zener diode maintains specific voltage across its terminals, and within the given range of line voltage change and load voltage change. So you can see here there are two words. One is the line voltage change, another is load change. So when you have a Zener diode connection, so the line voltage means the input voltage, and the load change, you can understand that is the output of a circuit. So in output of a circuit, load is connected. So that load can be changed because of some practical considerations. So whenever you change the load, then diode also this Zener diodes have capability to sustain for the voltage change and load change. So better diode have better sustainability, and if you take less costly diode, that will be having less sustainability. And it is mostly used in DC power supply design. So when I was discussing with you DC power supply, at that time I told that in voltage regulator, that is the last part of the DC power supply, there is the need of Zener diode. So this gives the stable power supply. Okay, so this is a construction of Zener diode. Here are P type material and N type material similar to the normal diode. So this is a round shape Zener diode, and the doping level is maintained or is changed to reduce the breakdown voltages. So in general, the Zener diodes are heavily doped. You can see here written that these are the heavily doped diodes. So these are generally heavily doped, so that if you want to reduce the breakdown voltages, so they have the doping has to be changed, because these are heavily doped, so therefore they have very thin depletion region. Okay, based on the doping level, other manufacturing parameters, there are two kind of breakdown mechanism you must have heard. One is the avalanche breakdown, and other breakdown mechanism is called Zener breakdown. Okay, so this is what, and avalanche breakdown occurs at higher voltage, and Zener breakdown occurs at lower voltage. So if you have a Zener diode having a low Zener breakdown voltage, then you might be facing Zener breakdown, and if you have a diode having more than 6 volt of Zener voltage or breakdown voltage, then that particular diode will have avalanche breakdown mechanism inside it. Okay, so let us see the Zener diode working. Zener diode works similar to the normal diode. The difference between the Zener diode and normal diode is that when it is placed in reverse bias, in reverse bias normal diode gets break and it doesn't work, but in reverse bias Zener diode works. So this is a special parameter, and operating range of Zener diode depends on its doping level and properties. So before applying a certain voltage to a Zener diode, you must have seen the data sheet up to what value this diode can bear up. So that must be known beforehand. So when you know beforehand how much value the diode can sustain, then only you should apply a particular voltage. Okay. Working of a Zener diode. So Zener diode working, you must be seeing this. These are the waveforms. So you can see here that the waveform, this one is in the, this region is similar to the normal diode, and so, up to a certain voltage, 0.7 volt, the diode is not conducting, and after cutting voltage V gamma, the diode starts conducting, and this conduction gives a constant value of voltage, and the current gets increased. In a reverse bias, you can see that to certain voltage, to this voltage, there is no current or very small reverse saturation current. So this is called reverse bias region, and in this region normal diode doesn't work. In this region is for the Zener. So you can see there is a shaded region for let's start the discussion over a new topic, that is Zener diode. So in this diode, you can see this portion is the reverse breakdown region where the Zener diode works. So this is the region of working for Zener diode. So here Zener diode will work. This is the reverse breakdown region. Okay. So this is the what is the difference between normal diode and Zener diode. And if I take an ideal Zener diode, then there will be difference in the characteristics. I will show you soon. And here in this slide, I have broken the Zener diode breakdown characteristics in detail. So you can see that when there is this is a shape is like knee of human. So this voltage is Zener voltage is also called knee voltage, and at this knee voltage the current flowing is called Zener knee current, and this when its current get increasing and without increasing the voltage, and the maximum current that is flowing through the Zener diode is called Zener maximum current, and the current between the knee current and the maximum current is called Zener test current. So in this way, this breakdown region is divided and analyzed. So this Zener diode voltage can be calculated by the doping level. So as I told already in earlier slide, means the Zener voltage depend on the level of doping. So here you can see that the Zener voltage can be controlled by the level of doping. Okay, so here you can see this epsilon is the relative permittivity of the material, which is equal to epsilon naught into epsilon r. Epsilon is naught is the absolute permittivity, and epsilon r is the relative permittivity of the material. And Ez is the Zener field. So this is calculated by change in the Zener voltage divided by change in the depletion width. So dV by dW, and this Q is the charge of electron, which is 1.6 into the power minus 19 coulomb, and capital N is the average concentration. So this average is the geometric mean of Na and Nd. So Na is the acceptor ion concentration in P side, and Nd is the donor ion concentration in N side. So Na Nd upon Na plus Nd. Na parallel Nd means Na Nd upon Na plus Nd. Okay, let's go further. This is the equivalent model of Zener diode. In equivalent model of Zener diode, you can see that there is a resistor and then there is a voltage. So this combination of resistor and the power supply is the representation of normal diode. Similar to normal diode, here is one resistance and one current, one Zener voltage. But always remember that this works only in the, and other thing is that there is Zener resistance. So Zener resistance is represented by this, and this is the Zener voltage. Okay, so how this Zener resistance is calculated? So here you can see in the shaded region, change in voltage upon change in current is the Zener resistance, and this power supply is equal to the Zener voltage. Always remember, Zener diode works in the reverse bias. Therefore, this all equivalent circuit will be for the reverse bias. Next is equivalent model of ideal Zener diode. So for the ideal Zener diode, there will be a sharp breakdown. So this will be sharply going down, and there will not be any resistance. Means current will be infinite suddenly. So the ideal Zener diode is represented by only a Zener voltage. Okay. So next, this is the practice problem. One Zener characteristics is given, and the current Iz and the corresponding change in voltage is mentioned in the characteristic. You have to find out Zener impedance. So it's a simple code problem, you can easily understand. These practice problems are for the Zener diode waveforms. So one sinusoidal input is provided, and here there is Zener voltage is diode voltage is 0.7, and the Zener voltage is something that is not mentioned. So you can see that positive side this clipping is at the Zener diode voltage, and in the negative side the clipping will be in the forward bias. So this is can understand here that Zener diode regulates in both positive side and negative side both. In positive side it regulates at 0.7 volt, in negative side it regulates at the Zener voltage. similar to that, if I connect Zener diode in the forward bias, so in the B figure, this is connected in forward bias. So the positive half cycle, this will be limited to 0.7 volt, and in the negative half cycle, this will be limited to Zener voltage. If I connect two diodes, one in forward, one in reverse, so we have to take one forward bias and one reverse bias in the both of the cases. In positive side also one forward bias and one reverse bias, and negative side also one forward bias and one reverse bias will come into the picture. Okay, so this is one problem. For your practice, you try to understand this and then you have to get it. And this is going to whenever there is voltage shown near to the Zener diode, that is called Zener voltage, and this is also Zener voltage. Do not get confused with that. This might be a forward cut-in voltage. This cannot be. This forward voltage cannot be more than this 0.7 volt. Therefore, whenever any voltage greater than 0.7 volt is mentioned near to a diode, then this voltage is cut-in voltage. So in the Zener diode, usually they mention their Zener voltage. So here you see that in the forward bias, there is not any mention of the cut-in voltages. Let us see, one diode will be forward and one diode will be reverse, and this will be 5.1 volt plus the voltage that is coming in the forward bias of our upper diode. So this is 5.1 volt plus 0.7 volt. So here we have to consider that these are the silicon diode. I'm not saying that these are the ideal diode, these are the silicon diodes. So because this is the silicon diode, so this 5.1 volt is in the reverse bias, and 3.3 volt diode is in the forward bias. So the total diode voltage is 5.8 volt, and in the opposite side, so this diode will be reverse bias and this will be forward bias. So total voltage will be 3.3 volt plus 0.7 volt, that is minus 4 volt. Therefore, this type of waveform is coming out of the picture. Okay. Next problem is this one. Next problem, these are the two voltages. So this is for your practice. You try to understand similar to the previous one. In one half cycle, in the suppose positive half cycle, and this is D1 and this is D2, and this is also of silicon and this is also of silicon. Total voltage will be 3.3 volt plus 0.7 volt, that is minus 4 volt. Therefore, this type of waveform is coming out of the picture. Okay. Next, and this is D1 and this is D2, and this is also of silicon and this is also of silicon. And because these both are of silicon, so in the forward bias, what will happen that this diode will be replaced by a 0.7 volt battery, and this diode will be replaced by a okay. So this is one practice question. You can see this is the answer. This answer how it is coming, you just see. And the Zener diode breakdown mechanisms are two. One is Zener breakdown and another is avalanche breakdown. Avalanche breakdown अलग तरीके से होता है, Zener breakdown अलग तरीके से होता है, और दोनों के बारे में मैं थोड़ा थोड़ा आपको बता देता हूँ कि Zener breakdown जो होता है वो एक लो वोल्टेज पे होता है, और लो वोल्टेज पे होता है। दूसरा, ये इसका जो प्रोसेस है, सपोज हमारे पास एक ये पीएन जंक्शन डायोड है और इसमें ये डिप्लीशन लेयर है, इसमें आपने रिवर्स बायस अप्लाई किया हुआ है, मीन्स पी साइड आपने नेगेटिव लगाया है और एन साइड पॉजिटिव लगाया है, और आप एक वोल्टेज को बढ़ाते जा रहे हैं। वैसे यहाँ पर नेगेटिव वोल्टेज बढ़ाते जा रहे हैं, पी साइड में नेगेटिव वोल्टेज लगाते जा रहे हैं। जब आप पी साइड नेगेटिव वोल्टेज लगाओगे तो ये इलेक्ट्रॉन पी साइड अट्रैक्ट होंगे और एन साइड के और यहाँ तो इलेक्ट्रॉन्स इस साइड जब अट्रैक्ट होते हैं, जब आप और वोल्टेज बढ़ाते जाओगे तो इलेक्ट्रॉन इसको डिप्लीशन विड्थ को पेनिट्रेट कर जाते हैं। तो जो प्रोसेस होता है, जो पेनिट्रेशन का रीजन होता है, वो रीजन होता है डायरेक्ट रप्चर ऑफ covalent bonds. So you can see the region, carefully understand the region, that this is because of direct rupture of covalent bonds. जेनर ब्रेकडाउन किस लिए हो रहा है? क्योंकि यहाँ पर डायरेक्ट रप्चर ऑफ कोवलेंट बॉन्ड हुआ है। अगली जो ब्रेकडाउन मैकेनिज्म है जो कि रिलेटिवली हायर वोल्टेज पे परफॉर्म होती है, वो है एवलांच ब्रेकडाउन। और एवलांच ब्रेकडाउन, let's start the discussion over a new topic, that is Zener diode of covalent bonds. जेनर ब्रेकडाउन किस लिए हो रहा है? क्योंकि यहाँ पर डायरेक्ट रप्चर ऑफ कोवलेंट बॉन्ड हुआ है। अगली जो ब्रेकडाउन मैकेनिज्म है जो कि रिलेटिवली हायर वोल्टेज पे परफॉर्म होती है, वो है एवलांच ब्रेकडाउन। और एवलांच ब्रेकडाउन में जो कंपैरेटिवली हायर वोल्टेज पे होता है, इसके प्रोसेस में होता क्या है कि एक कोवलेंट बॉन्ड ब्रेक होता है और वो एटम को भी साथ में कुछ एनर्जी प्रोवाइड कर देता है। ये हायर एनर्जी लेवल पे होता है। तो जब एटम को एनर्जी मिलती है तो ये 2-3 एटम्स को एनर्जी इम्पार्ट कर देता है, और अगेन ये सारे एटम्स फिर अगले एटम को एनर्जी इम्पार्ट करते हैं, और इस तरीके से एक चेन रिएक्शन टाइप का बन जाता है। और इस चेन रिएक्शन से सडनली डिफरेंट एटम्स की और एनर्जी बढ़ जाती है, और कम्प्लीटली आपका जो ब्रेकडाउन रीजन है या डिप्लीशन रीजन है, वहाँ पर एक बहुत हाई एनर्जी के एटम्स मूव करने लगते हैं, जहाँ से जो कि हाई करंट फ्लो को अलाउ कर देता है। तो एवलांच ब्रेकडाउन मैकेनिज्म थोड़ा सा जेनर ब्रेकडाउन मैकेनिज्म से डिफरेंट है, और जो हाई वोल्टेज पे परफॉर्म होता है। अब हम देखेंगे इनके डिफरेंसेस। इस एवलांच ब्रेकडाउन और जेनर ब्रेकडाउन में क्या डिफरेंस है और मीन्स क्या अंतर है। तो इन दोनों को मैंने डिफरेंट वे में कंपेयर किया है। पहला कंपैरिजन है उनके डेफिनेशन पे। एवलांच ब्रेकडाउन इज देयर ड्यू टू द कोलिजन ऑफ क्रिस्टल आयंस। मैंने अभी आपको बताया था दिस इज बिकॉज ऑफ द कोलिजन, एंड दिस इज बिकॉज ऑफ द चेन रिएक्शन बिकॉज ऑफ द कोलिजन, and in the Zener breakdown this is because of the direct rupture of the covalent bond, avalanche breakdown. So this is the one difference in the Zener breakdown and avalanche breakdown. Next difference is this chain reaction, that is in the this is in the pause the video and write the answer. This happens in, ये किस में होता है? ये Zener breakdown में होता है कि avalanche breakdown में होता है? ये आंसर आप लिखिए कि ये जो रिएक्शन यहाँ पे शो किया गया है किस में होता है। इसको आप लिख लीजिए, वीडियो को पॉज करके लिख लीजिए। अगर आपने ध्यान से इससे पहले का वीडियो सुना होगा तो डेफिनेटली आप यहाँ पे लिख पाओगे। एंड हियर आई विल से, सो अगर आपने लिख लिया है तो मैं बता देता हूँ आपको, ये जो रिएक्शन है ये शो कर रहा है आपको एवलांच ब्रेकडाउन। ये एवलांच ब्रेकडाउन को रिप्रेजेंट कर रहा है, और ये मैंने बनाया हुआ है डायरेक्ट रप्चर को दिखाने के लिए कि ये डायरेक्ट रप्चर से होता है। तो ये जो डायग्राम मैंने बनाया था जेनर को ब्रेकडाउन को रिप्रेजेंट करने के लिए, और ये दोनों ही ब्रेकडाउन जेनर डायोड में होते हैं। ये ब्रेकडाउन जेनर ब्रेकडाउन और एवलांच ब्रेकडाउन दोनों ही, वो डिफरेंस है वो है इन एवलांच ब्रेकडाउन इलेक्ट्रिक फील्ड इज नॉट रिक्वायर्ड, एंड इन जेनर ब्रेकडाउन वेरी हाई इलेक्ट्रिक फील्ड इज रिक्वायर्ड। सो बिकॉज जेनर डायोड occurs in the at the less voltage, so it works in very high electric field. And next one is the avalanche breakdown is based on low level doping, and Zener breakdown is based on the high level doping. Zener breakdown लो लेवल पे होता है, बट उसमें हाई लेवल की डोपिंग चाहिए होती है, क्योंकि जब आपके पास थिन लेयर होगी तभी ये लो लेवल पे पॉसिबल है। तो थिन लेयर करने के लिए आपको हाई लेवल डोपिंग करना ही पड़ेगा। थोड़ा अगर आप कनेक्शन करोगे तो ये बहुत आसानी से याद रख सकते हो। अगर आप कनेक्ट कर पाओगे कि थिन लेयर क्यों जरूरी है, और थिन लेयर के कारण यहाँ पे लो वोल्टेज पे ब्रेकडाउन हो पा रहा है। ओके, अब हम देखते हैं कि टेम्परेचर कोफिशिएंट जो होता है एवलांच ब्रेकडाउन का पॉजिटिव टेम्परेचर कोफिशिएंट होता है, और जेनर ब्रेकडाउन का नेगेटिव टेम्परेचर कोफिशिएंट होता है। ओके, यहाँ पे आप देख सकते हो टेम्परेचर का इफेक्ट। So T2 is greater than T1. T2 is for avalanche breakdown and T1 is for the Zener breakdown. So you can understand this, that this Zener breakdown is temperature as compared to the avalanche breakdown. So avalanche breakdown is used in the graded junction like semiconductor diode, BJT, FET, MOSFET, and Zener breakdown is used in the step graded junctions like tunnel diode and Zener diode. So these are the applications of avalanche breakdown and the Zener breakdown. Okay, so now the question is, why Zener diode is used as voltage regulator in DC power supply? You can write in your notebook one answer for this. And another question is, what is voltage regulator? And another question is for you, that is, can we use normal diode as voltage regulator? If yes, then why and how? Can we use normal diode or rectifier diode as a voltage regulator? And if no, we cannot use, then why we cannot use rectifier diode as a voltage regulator? Watch the next lecture, next video to get answers of all these questions. I will explain these questions in the next lecture. Okay, thank you all, thank you so much, thanks for watching.